I'm Daniel Ehrenberg, and I work in TC39, and I came here to tell you about BigInt. But first, let's talk about numbers. Math.pow is this function that can take a number to a particular power. So here, x will be 2 to the 53rd power. Actually, now you can just write 2 to the star 53. So what does that equal? This huge number starting with a 9 and ending with a 2. What do you get when you add 1 to that? So this 2 to the 53 plus 1? The same number back, this huge number starting with a 9, ending with a 2. What? What's going on? So in this talk, I'll tell you about why numbers do this, how we can fix this using BigInt, and how TC39 has been developing BigInt in partnership with the JavaScript community, and how you can get involved to shape the next version of JavaScript. I really want your help in all of this. We can't do it without you. So first about numbers. Numbers in JavaScript are 64-bit floats, floating point binary numbers. So that's basically like scientific notation. Remember from grade school, 30,000 you could represent as 3 times 10 to the 5. And here the exponent would be 5, the sign is +1, and the fraction is 3. And IEEE 754 floating point numbers are just like that, except it's base 2 instead of base 10. So we have the sign, which is 1 bit, and we have the exponent, which is 11 bits, and the fraction, 52 bits. So our friend 2 to the 53rd power looks like this when you put it in a floating point. Sign is 0 to represent +1. The exponent is that number starting with a 1, and the fraction is all zeros. It has an implicit sort of 1 point before the zeros. The next biggest number is actually that ending with a 4. If you look at the last digits, the last digit of this number ending in a 2 is 0, and the last digit of the one ending in 1 is 1. There's actually no numbers in between. When I say number, I mean these binary floating point numbers. Ultimately, if we're representing something in 64 bits, there's only 2 to the 64 different bit patterns. So we can't represent every single actual number that exists in the world, or every single integer even. At some point, we have to round or go up to infinity or have an error. But this seems like a pretty random edge case. Does this ever actually come up in practice? It turns out it does. So in Twitter's API, there's an ID field. Stuff like tweets are represented by JSON objects. And the ID that you get over the network might look like this big number ending in 888. The thing is, when you parse that in JavaScript, it gets converted to a number. So the 888 rounds to 900. For this reason, Twitter includes a secondary field, ID string, which is a string of the number. And that doesn't round. But people run into this as a problem all the time. Like, it's kind of easier to just use the ID rather than the ID string. And it's hard for Twitter to remove it because of compatibility. Sometimes the numbers don't overflow, like in that second line in this bug, but other times they do. And you just are referring to the wrong object. Another case this comes up is in inode numbers. So in file systems, each file is generally associated with a number, which is sort of like a pointer to the file. And Node.js includes an API called stat to read the inode number of a file. On Linux, the inode numbers are often kind of low, but on Windows, they can sometimes be really high and run into the same kind of rounding issue. So this lstat sync, there's actually a reproducible test case where you can create a folder and create a couple files in that folder which have inode numbers, which one of them ending in 27, but then it rounds up to 28, and another file in the same folder has an inode number in 29, but then it rounds down to the same 28. So if you try to pass those inode numbers back to the system again, it's just not going to work. It's just the wrong number. To get around these kinds of problems, developers have created libraries like bn.js, which has millions of downloads every week and gives you an object API for this, where you can instantiate a new big num and call methods on it to add or things like that. But there's some limitations here because it's not as integrated into the system. So if you have something else in the standard library or in the web platform or Node, it's not obvious how to integrate with this. It's not as optimizable because the JavaScript JIT doesn't know about it. So the JavaScript engine can't use knowledge of mathematics to make it faster. And it's also just an extra thing to download and integrate, which is difficult in some projects. So what if we had this in JavaScript itself? Going back to the original example, where we add 1 and we get, the same number back again. What if we could indicate that we want to refer just to integers using a suffix like n? So 2n to the 53n would be the same number, starting with a 9 and ending with a 2. But when you add 1 into it, you'd get a 3 at the end. And n here, so the 2 goes to 3. N here stands for BigInt. But is this JavaScript? It is, soon. BigInt is at stage 3 in TC39, and we're adding it to the JavaScript programming language. Actually, it's shipping in Chrome now as of a few days ago. BigInt is shipping in Chrome 67, and in Node Master, BigInt is also supported. BigInt's being developed in Firefox and Safari as well, and it's on the roadmap for Edge. But who is this TC39, and what are they doing to my JavaScript? So remember ES6? ES6 gave you nice features like destructuring. So if you have 2 variables, x and y, you can swap them by putting an array on the left-hand side and just swapping them. And so this and other things like async await were all added by TC39. TC39 is a standards committee that's part of ECMA. And ECMA is this standards body based in Geneva, sort of for administrative support, but then we in the committee are JavaScript developers, implementers, people who are making JavaScript work in web browsers and Node and Babel, framework authors like Angular and Ember and React, and academics who have a background in programming language theory and more. And we all get together to produce this document, the ECMAScript language specification. If you were going to print this out, it would be 1,200 pages. It would be, or more than 1,200 pages. I recommend just looking at the website. It has these nice searching features. We developed this document on GitHub. It's an open source project like any other with issues and pull requests. And we also develop it at meetings. So here there's a part of an agenda for the meetings. We always seem to run over a little bit on the agenda. But we meet every 2 months for 3 days, and we talk about the activity on GitHub. And we also talk about new proposals for extending the language. And these proposals move through stages. So if it's a big proposal like BigInt, we don't just have a pull request against the main spec and start with that. We instead make a separate proposal that goes through these stages. You might have heard of stage 1 is just a general idea. We're discussing sort of a problem space within the committee. Stage 2 means that we have an agreed on first draft that TC39 has decided we're going to do something here, and it's going to look more or less like this. By stage 3, all the details are worked out, and we have a complete first specification, and it's ready to go off to implementers. And by stage 4, we have multiple implementations and lots of feedback from real usage, and so we're ready to just make it part of the actual JavaScript standard. So how did BigInt go through this process? Actually, BigInts or Int64 has been in development for longer than the stage process and longer than Chrome and Node. Back in 1999, just a few years after JavaScript was created, long and ulong types were proposed. And so these would hold signed or unsigned 64-bit integers. But they never quite made it in. So in ES3, that update was mostly expansions to the library, like regular expressions. ES4 was this huge project that also was thinking of adding these types, but it got so complicated it just had to be abandoned. And in ES5, to sort of recover from that, to heal from that process, the language changes were really minimal and included things like cleaning up the object model and eval and a few other library additions. Then ES6 made a whole bunch of changes, such as this destructuring assignment that I just mentioned. As part of ES6, the committee was talking about adding value types, which would have been user-defined data types, so user-defined primitives. You can already define your own objects, but there's no way to define your own thing like number as a JavaScript programmer. And we're still talking about doing value types, but they weren't added in ES6. They're deferred until later. So long history of not yet doing larger integers. But then recently, in November 2016, Brendan Eich proposed again to the committee that we do int64. Rather than coupling it to the whole value type package, int64 and unsigned int64 was proposed as a standalone proposal to just add this one new primitive type. By the following January, we settled on, actually, we want to do this as BigInt rather than int64. I'll talk about the reasons more in a bit. And then by that July, we got to stage 3 in the process. And now it's shipping in Chrome 67. So let's go over how this went in more detail. So for stage 1, the big thing you need for stage 1 is to have a description of the problem and the motivation. So what we did in TC39 was create this proposal repository, just a GitHub repository, proposal BigInt, and made a README file that has some code samples for how it might look, has some motivating use cases, and some ideas for what the semantics would look like. We also opened a bug tracker in the same repository and invited various community members to participate and give opinions about various different semantic points. So a couple of the big discussions that we went through were BigInt versus int64. So I mentioned in the history that much of the time we'd been discussing adding 64-bit integers to the language rather than adding arbitrary size integers. And some of the reasons for that were some people felt like it would be a more minimal addition. So if you have a 64-bit integer, then it will just overflow or throw an exception when you get out of bounds. That could work. For a lot of the applications, it works. The whole point of the proposal is to avoid the overflow, but sometimes 64 bits is enough. And people thought that this would be maybe easier to convince browsers to implement, or it might execute faster. But when we talked more with the browsers, actually Benedict Meurer from the V8 team sort of led this effort to reconsider arbitrary size integers. This way, you never have to worry about overflow. And it actually turns out that the way that modern JavaScript engines work, they have machinery for doing all this sort of optimization for working with numbers in particular ranges to convert them to integers. and at the same time, int64 wouldn't be that fast without all sorts of optimizations, because it has to be allocated in the heap. You have to do all sorts of type checking, and to get it to the point where it's actually sort of allocated in registers or on the stack, there's already a lot of magic going on. And when that same magic is applied, it would work for BigInt. So we decided to, bite the bullet, solve the whole problem better, and go with BigInt rather than int64. The other big semantic point that we discussed was what to do with mixed types. So in a language like Python, you can just add a large integer and a float, and you get a float back. And what we decided for JavaScript is we don't actually want to do that. What we're doing instead is, the whole point of BigInt is to be this new data type that provides this mathematical accuracy. You don't have to think about all the complexity of IEEE 754. You can just think about integers. But what integer would you get when you add a very large integer, 2 to the 53 plus 1.5? The answer isn't actually contained in the set of integers or in the set of representable floating point values. So what we decided is, rather than come up with the wrong answer, when the whole point of the feature is to come to the right answer, we would throw a type error in this case. And we would just say, we're not going to come to an answer. So actually, you can't mix BigInts and numbers in general in mathematical operations. And this leads to a best practice that I'd recommend. BigInts are good when you have a value that ranges that might be larger than what can be represented in numbers. But if numbers are working for you, stick with them. Numbers still work just fine for small integers. And in general, because we have to make this decision up front, it's because of that issue I just described. Numbers in use for what they're in use for right now just still works very well. So to get to stage 2 from there, the committee wrote this draft specification document. And this is just like the main document for the whole specification, except that it's only the segment that relates to this new feature. So it includes sort of some insertions and some deletions and some new sections, but you can ultimately read it in the same HTML file. And that's generated from this specification format. This was created by Brian Turleson and Ron Buckton, this EC markup tool that lets you use a combination of Markdown and grammar syntax to easily generate these specification drafts. My coworker Robin Templeton at Igalia also started around this time implementing BigInt in SpiderMonkey, which is currently, starting to land. So even though stage 3 is when something is really, really ready for implementation and really stable, it's never too early to get started prototyping. And this process helps the development of the feature. To get to stage 3, we needed sign-off on this specification. So in particular, a couple committee members, or sometimes more than a couple committee members, volunteer to read the whole specification in a lot of detail, as well as the editors, and see whether it's ready. So this leads to a lot of typos being fixed and cases being looked at closely. And once we got to this level of stability where the committee signed off and the committee is really saying, yes, we want to do this feature. Stage 2 is, yes, we want to do this feature. And stage 3 is, we want to do it this way. And we really need implementation feedback. So this level of stability led the V8 team to implement BigInt. And following that, thank you, Jakob Kumaro, for great work leading the BigInt implementation. And also, Kaio Lima worked on BigInt in JSC, which is in progress. Even once we got to stage 3, even once we said that we had this level of stability, there were still some edge cases that people came across that, because the feature hasn't shipped to the web yet, we were open to revisiting. So there were tons of different edge cases like this that we spent committee time on before getting to stage 3, and then even after stage 3, we looked at this one. So, double equals and less than. In JavaScript, you can use them to compare a number and a string. And when you do that, it converts the string to a number, and it compares them as numeric values. So, this is part of JavaScript being maybe weakly typed and having all these casts everywhere. And so to make sure that BigInt is consistent with numbers, we did that same behavior in BigInt. But we accidentally, in this second case here, we're converting the BigInt to a number, and it would compare as less than when it's actually the same value, because that number would be rounding down. To get to stage 4, what we're going to need is full test262 tests. There's a conformance test suite that verifies that that implementations are working right. So we have those conformance tests. A pull request to the main specification to pull this in. Well, there's still a little bit more refactoring to do for that. And then 2 implementations where we have one full implementation, but the next 2 are still in progress. So maybe we'll get this by ES 2019. We'll see. Or maybe ES 2020. I hope so. So to let you know how to get involved, there's just a lot of different ways to get involved here. Feedback on GitHub issues is really great. I'd love to hear about whether a feature proposal works for you, if there are pieces missing, or if a case should be handled differently. And this was really useful for working through tons of issues with BigInt. Test262 tests. There's this project to implement tests for the JavaScript language itself. And it's an open source project that's happy to have new contributions. What we find is that when something is missing from the test suite, actually different browsers or different JavaScript implementations have different behavior because different people end up reading the same specification differently by accident. And so it's really important to have a full test suite. There's other parts, other standards have other tests like web platform tests, and we have Test262. And so, for example, here's a pull request to add tests that check that adding a number in a BigInt throws a type error. And for the BigInt project, Test262 helped make implementations correct the first time and stay correct. Sometimes, Maya from the V8 team made a joke to me. Sometimes implementations make so many optimizations that they optimize away the specification itself. And so this helps prevent that. Even as you're maintaining the project, then you still have all these very complete correctness tests. But it went even further than that, because the people working on these tests took a really close look at all of the edge cases and helped work through a lot of the design decisions. And more than 6 test engineers collaborated, especially engineers from Boku and Igalia. We're also happy to have help on documentation and education. So with this README file, a number of people contributed, and it's really important to understand the different mental models that JavaScript programmers have. People aren't programming thinking through the entire specification, and different people have different mental models. So this is especially useful. We try to compare a bunch of different ways of thinking through code when designing language features. So for example, in the BigInt design process, Ashley Williams pointed out that when learning programming, a lot of programmers have an intuition that variables should have particular types. So this made us feel not quite as bad about not permitting mixed operations between BigInt and number, because this is actually a pretty intuitive thing for people to learn, that a value has a particular type. It's also welcome to implement things, so you can contribute to any sort of lots of different implementations of JavaScript. And through implementations, it's not just about getting JavaScript to developers, but all these 3 implementations of BigInt that are in progress or complete contributed to the design of the feature. It's also possible to, if you're not able to do this development yourself, companies like Bloomberg and Google sponsor work to push these things forward. And of course, in these meetings, we're open to new members. So, let me know if you want to get involved as a TC39 delegate. It's an organizational membership, so something like your employer would join, or there are also nonprofit memberships. So, as a takeaway, please, if you're interested in building the future of JavaScript, get involved in TC39. You can go to our website, and now you have BigInts, and use BigInts for integers which may be very big, and use numbers for numbers that are smaller. So I'm Little Dan, and thank you.